Hello, CheersKevin here, and we're back programming with kOS. Today we're going to get our autopilot executing maneuver nodes. And to do that, we need to leverage some of the KSP bindings. So what the heck are those? KerboScript is a programming language, which means it has things like variables and loops and functions for us to play with. And we can write all sorts of fun and complicated programs. But what makes kOS an autopilot system are the KSP bindings, built-in keywords and utilities that let us control our craft in-game. To use an analogy, consider a computer printer. Microsoft Word or Photoshop or your browser are all able to send jobs to your printer, but none of those programs are necessarily written with your printer in mind. Instead, they use a driver. And a driver is nothing more than an interface that allows us to get information to and from a device. In the same way, when we're writing KerboScript, we have built-in utilities like lock steering or the node function to give us a maneuver node. We don't have to know the details of how Kerbal Space Program was written in order to perform these functions. kOS provides these KSP bindings for us. Now, for the most part, kOS is going to provide us with what it calls structures. A structure is a set of variables and functions that logically go together. To use an example other than the maneuver node, kOS provides us a structure called a vessel. We can ask about the vessel's mass, its available thrust, and it can even give us back other structures. We'll get back a vector if we ask about its angular momentum. The goal today is to plug the holes in our program, functions that we mostly left empty. Since we'll be relying on these structures, we're going to spend a fair bit of time in the kOS docs. The developers have put in a ton of time into making these clear and readable, and these docs serve as the formal contract for how we can actually affect our surroundings in KSP. So don't forget to add a bookmark. So we're going to operate in sort of a split screen mode this time, and I apologize for those of you watching on very tiny screens, but it really is going to save us so much time. I've got the kOS docs open on the right and our code here on the left, and we've commented out all of our launch and ascent stuff, and we're just worrying about this execute maneuver function. Now, if you remember in the last video, we did kind of scope out the skeleton of how this works. Now we're going to be mainly dealing with these structures that kOS provides us that allow us to interact with KSP, and that's the whole point of writing this stuff, not so that we can display some fancy text on the in-game terminal, but so that we can actually control our craft and do things like that. And we end our commands by using the period key. You may have noticed something a little odd in that even looking through this sort of skeleton code that we started to write, we say wait until time seconds is greater than start time. This whole process for executing a maneuver, this colon is rather odd, and you'll see it in a couple of places. Why are we saying time seconds instead of, elapsed time or something like that? The reason for that is that this is actually a KSP structure. Time is a time span structure. It's a very special one, but it's a time span structure, and seconds is one of those variables that is part of that structure. We can actually look up time in the docs, and if we look at time span represents simulated time. And I'm going to go ahead and, there we go. Special variable time, access get only, and the type is a time span. So there we go. And we can see that this is the structure time span, and it has these various suffixes. So we can say time clock, and that would give us back this string of hours, minutes, and seconds. We could say time calendar, and it would give us this. We could say time seconds, and it gives us this scalar value, which is the number, which is what we ended up wanting. But that's the syntax that we're going to be using whenever we're dealing with these structures that are provided to us from kOS. So I'm going to go ahead and just click here to remove that. If we click down into structures, you can see there are a lot of these. And these are the ways that we either get information about the KSP world, or we give information about what we want the KSP world to be doing. And you can see if you scroll through here, there are a ton of different types of structures. We're going to be focusing on the maneuver node, because that's what we're mainly dealing with today. And in each of these, in addition to generally having that little table, which I think this one has, down here, having that table of all of the suffixes, assuming that you have a maneuver, these are all the things you can ask about it. So you do :delta-v or :burn vector or :eta. In addition, a lot of these will have some additional description or code samples up here at the very top. So this gives us a description that, hey, this is a planned velocity change along an orbit. It gives us some information saying that, hey, if you're not on the current craft, if you're trying to access a maneuver node from a nearby craft, KSP forcibly removes that, so blah, 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 blah. Not something we have to worry about, but this is one of the reasons that it's very useful to look at the docs for each structure that we happen to be using. So in this case, we get the creation documentation that says node, and it says, okay, well, I need a universal time, I need a radial, normal, and prograde, and it's telling us, hey, I expect this :v in meters per second, I expect this universal time in seconds, and blah, 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 and it returns a maneuver node. Now, any time that you see these these capitalized nouns, we can click on it, and generally we're going to get to this list of things, because this is the description of that structure. And if we look at the code example here, it says set x to node time seconds plus 60, 0, 0, 100. And that's saying, okay, create a node 60 seconds from now with prograde 100 meters per second. Well, that makes sense. We have something similar in our code already. We have node with some time that we're accepting as an argument, and radial and normal and prograde, and we're assigning that to this word maneuver. And here they're setting it to x, but that's fine. And they actually tell us here, hey, this is how you add a maneuver to a flight plan. Well, that's perfect, because we have a function that, well, we didn't know how to do this thing in kOS, so that's fine. We can actually fill out the body of this function now. I don't know, it shouldn't be highlighted, well, whatever. We'll go ahead and, let's see, we took in the maneuver as a parameter. We'll go ahead and just say add MNV. And then we'll save that. And now that function is done. We don't have to worry about it anymore. We have learned how to add a maneuver to a flight plan, and in fact, we could go through and say, hey, rather than actually calling out to this function, since it's just a single line, we could just replace this whole line with add MNV and get rid of this entirely. And if that's your taste, you're certainly welcome to do that. I actually don't like add, because I think it's a little bit ambiguous. If I were to say add foo, I don't know what this is actually doing. It's not intuitive from the name that it's adding the thing to the flight plan. So I actually like having the function here there, because I think it makes this execute maneuver a little bit more readable. So next on our list is this calculate start time function. I'm just going to keep these docs up here, and we can kind of refer to them as we're writing our code. These, we have 4 functions left. We had 5, and we've got to kind of figure out how to solve these small little problems. So this is calculate the start time for a maneuver node. So we get a maneuver, and we need to figure out when are we supposed to start burning that maneuver. Right now we said return 0, which isn't particularly helpful. So we'll go ahead and get rid of that line, and we'll get rid of this to do as well. And let's see. So the start time it's got to be relative to the universal amount of time. And if we go back to look at that time span structure, and if we look at, and actually I'm going to just click time span here, we see seconds. Total seconds since epoch includes fractional partial seconds, and that is what we actually want. So we want to get, and even up in here in the comments, it says total seconds since the campaign began. So we're going to be calculating some sort of offset from the current time. So we'll say time seconds plus something. Now, something is going to have to do with however long it is until we get to that maneuver node, right? Well, if we look here, that's already available, right? ETA, time until this maneuver. And now that's not the time of this maneuver, but it's the time until this maneuver. So we can go ahead and just access that suffix. We have a node structure, a maneuver node structure assigned to MNV. So we can use that colon and then just say ETA. And then dot. So we're going to add the current time plus however long it is until we hit the maneuver. Now, that technically could be a great start time, but I'm going to subtract something because, hey, we don't want to fire exactly on the maneuver because it may take us a little bit to execute the maneuver, right? So let's subtract, what are we going to subtract? It's going to vary based on what the maneuver happens to be. So this is a case where this function really needs a function of its own. We need to figure out the maneuver burn time for a particular maneuver. So we want to wait until the maneuver has arrived, but we want to start a little bit early based on the maneuver burn time and then divide that by 2. So we'll split the difference. We'll say if it's going to take us 10 seconds to execute the maneuver, we'll start 5 seconds early. That's not a perfect solution, but it'll do. So we'll go ahead and for the moment, I'm going to create a maneuver burn time and I'm going to say parameter maneuver. And here again, I'm going to cheat. I'm just going to return 10, and I think we can leave that there, at least for this episode, because it's reasonable. We'll just say, hey, we're going to assume it's going to take us 10 seconds to burn, and it's enough to at least get us moving along. We can come back and revise this to be a little bit smarter next time. And now at this point, we have 3 remaining functions that we had to fill out. So lock steering at maneuver target. This is one where, hey, we need to point the vessel at wherever we're supposed to be pointing it, and we didn't know how to do that, so we created a function. We don't have to worry about how it's actually called in that upper function. We're just trying to solve this individual problem. So let's look at our structures here and see if anything pops out. So let's see. Oh, here's one, the burn vector with a magnitude equal to delta V. We don't even care about the magnitude of the vector. Remember, a vector is a direction with magnitude. We're not going to worry too much about that. We're not going to get into too much mathy math stuff yet. Burn vector or delta V, and it looks like it says it's an alias. So they're the same thing. It's just 2 different words so that if we want to use one, we can use one. If we want to use the other, we can use the other. So all we need to do is lock our steering to that vector. Now, if we click on vector, we can find out information about the vector. We can get the direction. We can also get the magnitude. And the direction is its own thing. And we can go through all of these different structures and find out more and more information. For our purposes, it's just worth it to know that we can lock the steering to a vector. That's something that I'm just going to have you take on faith from me right now, and we'll get into that a little bit later. So I'm just going to say lock steering to MNV colon, and I'm going to choose burn vector because I think it's a little more readable than delta V. So we'll lock the steering to the burn vector, get rid of that to do, and now we're done with that little function. Is maneuver complete? That one seems tricky. Let's skip over that. Remove maneuver from flight plan. This is one where presumably we've got some sort of way of doing that, except that we really don't, because it's not an operation on the maneuver structure. It's an operation on our flight plan. So there's not something in here. It's not a suffix of that object. But we can see up here there's an example. It's just a simple keyword, remove, and then the name of the structure. So that's pretty easy. We'll go ahead and say remove MNV, and then we're done. Now this one is a little challenging because it's not something we just sort of get from this structure. The maneuver node represents a target change in our velocity, but it doesn't really have anything to say whether we're done or not. It tells us we can find out, hey, when did we plan on doing this? What were all the various components? What is the normal delta V? What is the expected orbit after we've completed this maneuver? All of this information, but it really can't tell us information about our specific craft because that's outside of the scope of this structure. So we need to be clever and come up with some sort of way of determining whether or not we have executed this. Now, if you like vectors, then that's fantastic. If you're not a fan of vectors, that's also fantastic. We're not going to worry too much about what a vector actually is, but we can use something about vectors if we think of them as just sort of arrows floating in space. We can consider the properties of some vectors to figure out, is our maneuver done? Because if we just look at how much delta V is left in the maneuver or something like that, well, if we overshoot it, the maneuver happens to update and say, hey, you should fire in the opposite direction. So if we overshoot it, we may never end up finishing our maneuver. So instead, what I'm going to do is I'm going to sort of pseudocode this. So we'll say, what was the direction to start with? And then I'm going to say, hey, how much have we diverged from the original direction? And is it a lot? Then we've overshot / are done. Right? So that makes sense. If we start firing in this direction, and we keep firing, and now we've overshot, that target is slowly going to move a little bit, and eventually, if we overshoot it, it's going to be pointed behind us. I can type arrows, and then we'll go, hey, the angle between these is significant, and so we must be done. And if we catch that early enough, we're not going to end up overshooting by too much. So that's a little hacky, but I think we can do it. So let's look and see if we get anything from vectors that allows us to do this. Now, the vector itself doesn't have a lot. It's got an x, a y, and a z, a magnitude, a normalized vector, blah, blah, blah. This isn't helpful. If we scroll down, though, there are some operations and methods that we can perform on vectors. These aren't properties of the vectors, but they're things that we can do to them. We can add vectors and multiply vectors. And here's one, vang, or vector angle. Now, if we look here, vector angle, it takes in one vector, takes in another vector, and gives us the angle between those vectors. Now, it doesn't say down here, but it does say up here that it's giving us a scale, and it's giving it to us in degrees. So, especially given that we're locking our steering to the maneuver, we'll figure out when we overshoot. So what we want to figure out is whether vang of the original vector and the current vector, let's say it's greater than 90. So if we've diverged a lot, then yeah, we're done. So we can go ahead and say return this. Now, of course, this is an expression. We could just write this instead as if this, and then say return true, else return false. Or we can just return this thing itself. And then get rid of this whole return true thing. Now, of course, I've just sort of assumed that there are some named things here, some variables. We actually have to get them somehow. So the original vector and current vector, thanks for this information about vectors, but we need to go back to our maneuver node to figure out how we actually get those vectors in the first place. And in this case, well, we can just look at the burn vector. So the burn vector, let's say a local current vector is the burn vector, the maneuver's burn vector. The original vector is something else. And to do this, we're going to have to use the same sneaky strategy that we used for auto staging. We'll say, hey, at the first time that this is called, it's not going to exist. So we'll go ahead and just assign it to maneuver burn vector. But on subsequent calls, then we can actually clear it out. So to do this, I'm going to scroll down a little bit. We can look at our do auto stage, and we'll just copy the bulk of this here, if not defined old thrust, because we were comparing old thrust and the current thrust. We're doing effectively the same thing here, just with the original vector and blah, blah, blah. So we'll take that, we'll say original. If not defined original vector, declare global original vector to maneuver burn vector. Now we have this original vector, and that's great. And in fact, because we assign this variable and then use it right away, I'm just going to replace it with what this actually is. So we'll just, instead of assigning it a variable name at all, we'll just say, hey, we're going to return whether or not the original vector has deviated by 90 degrees or more from the original vector. Now, there's one small, tiny little problem, and that is that if we call this multiple times, if we were to execute a series of maneuvers, well, then this original vector is going to have some memory of the last time it happened to be called. So in fact, even though I said we can go ahead and return whether or not this is true or false, I actually am going to put this in here. So if this, now what I want to do is I want to remove this. So I'm going to write a comment, delete original vector. So that way, next time this goes through, it'll assign it to whatever the new maneuver happens to be. And then we can go ahead and return true. And then at the bottom here, we could say else return false. Well, we could also just say return false, because if we've gotten in here, then we've already returned, so we don't need to have that else condition. Now, one small challenge here is I don't know how to delete a global variable, and I'm not entirely positive that it can be done. So I'm going to Google in here defined. Well, I'm going to Google. I'm pretty sure that this delete keyword actually refers to deleting files on the operating system. I could be wrong, but just to be safe, instead of actually deleting this, what we'll do is we'll assign it to a bad value. So we'll say, I'll use declare again. Declare global original vector to -1. So that's not a real vector, and that's great. So this, if we tried to use that, that'd be a problem. And then up here, instead of just saying if it's not defined, we can also say or original vector equals -1. So if either of those two things are true, then we need to pick up the maneuver burn vector and assign it to our original vector. Now that is it. We have this function written. We have all of the functions that had to-dos fully written. And I hope that this has shown a little bit of why it's useful to go through these docs. They have a lot of code examples. They have very great descriptions of all of the structures. And of course, the structures are the only way that we interact with the KSP environment that we're running in. It's how we get information. It's how we set information. And of course, there are additional structures in here that have nothing to do with KSP itself. There's something called a list, which is what you would imagine, a list of a bunch of different things, or a lexicon, which has keys and values, ranges and stacks, and lots of fancy stuff. It's fun to just scroll through here and look at all of the assorted different things that exist in here. But with all of that code written, I think it's probably time for us to jump into KSP and give this a test. Now in my case, I already have this circularized flight in progress. If you don't have that, then you'll need to go through and uncomment the actual launch code that we have in there. But I'm gonna go ahead and fly, and in theory, this should pick up that execute maneuver, and we'll see what it does. Oh no, it crashed. Well, that one is the unexpected token plus found after time seconds it expected a period, and the reason for that is a little non-intuitive. But we can see here we have parameter maneuver and then time seconds plus blah, blah, blah. We're not actually returning it. We need a return keyword there. Otherwise it's saying, what about time seconds? It exists, sure, but then you gotta put a period after the time seconds isn't something I can just exist on its own. So let's go and tidy that up. So that was in our, let's see, calculate start time. We'll return, and let me just verify here. Yep, in our maneuver burn time, we remember the return keyword. And let's just look through here. None of these actually have. This one does have the 2 returns. Remove maneuver doesn't return anything. So yeah, we should be hopefully good. Let's jump back over and see. And look at that. It has added a maneuver to our flight plan. So that's great news. We can see that's already here. And that's what it happened to do because we gave it some random values. We said, hey, I want this to happen in 30 seconds, which means that it should start, I think, 5 seconds before the burn. That's what we put in there as a reasonable default. We said estimate that the time it's going to take is going to be 10 seconds. It is steering and it is executing that burn. It's not staying on target very well, but hey, it's done. It proceeded and ran. Oh, okay, there we go. Right, because it hit my map view. We have this thing actually running maneuvers, and that's pretty sweet. Now, of course, it's doing it in a way that's a little haphazard. This is not necessarily, we've locked the throttle to 1 and then we locked it down to 0. If we were to roll that back a little bit, we could be more reasonable. If we were to calculate how long it's actually going to take us to execute the maneuver, then we can do that more reasonably. But this is a good first start. We'll see about using math to optimize things in the next episode. I'll see you then.